Last week we wrapped up transformations. So the graphs that we're talking about today, we will not be transforming. All we're doing is coming up with their inverse graph. And then this is where we'll be wrapping up graphing for this unit. Okay? We have 2 more lessons that we'll be completing for Unit 2, Part 2, and then we'll begin reviewing for our test after today. But this is the last bit of graphing that we're going to do. So, it says we are going to be graphing inverses. So, first, they give you a function that you're super familiar with, and they just want you to graph it. Okay, well, any function that has an x squared is just our parabola, right? And that parabola normally has its vertex at where? At where? 0, 0, right. Normally at 0, 0. But this one says that it was moved to the left or right? Right. To the right, and up or down? Down. Okay, so that 0, 0 has now moved right 2 and down 3. Right? Okay? And then from our vertex, as long as there has not been any type of stretch or compression, to plot the next point, we usually go up and over 1, both directions, right? Okay, well, I look for an A or a B. It does not appear that we have either one of those. So I am just going up 1 and over 1, both directions. Okay, now remember your function is squared, right? So whatever number you're plugging in, that's what you are squaring to get your output. That's why whenever I just went right 1, so if I plug a 1 in, right, 1 squared is 1. That's why I only go over 1 and up 1, right? What if I plug in a 2? What's 2 squared? 4. So that tells us that our next point should be to the right, 2 up 4. And then same in the other direction, right? So if I plugged in -2, I'd have the same outcome. Okay. All right, so that's enough points for us to get a pretty good idea of what this graph looks like. And like we said, it's that parabola-like shape, so it looks something like this, right? Okay, so we are just going to list all of the coordinates for this graph over here in this table. Okay, so let's see. The first point, if we're reading from left to right, would be this one here. And where is that coordinate point at?
0, 1.
0, 1. Okay, so I'm going to put that point in my table. Okay. Next point, as we're reading left to right, we come across will be this one down here, which is at 1, -2. All right, and then our vertex down here is at 2, -3. All right, and then we have a point mirroring that 1, -2, and that point is at
4, 1.
Shouldn't it have gone like to the right twice instead of like going to the right once?
What are you talking about?
After like the 1, 1, shouldn't it have gone like 2, 2, 4? Or is this
2, 4. Yeah, so I went over 1, 2, up 1, 2, 3, 4.
Oh, that was. Okay.
Okay. So that next point that I put the red dot on would be at 3, -2, and then that last one is at 4, 1. All right. You start at your vertex every time you count. Okay. So for this picture, what would you guys say that the domain is? All real numbers. Okay, so it's never going to stop going to the left or right, so all real numbers. All right, what would you guys say the range of this function is? Is less than or equal to? Greater than, right? Because it's going to keep going up. Good. All right, so y is greater than or equal to -3, because the lowest point was at -3, and then it continues upward from there. Good. Okay. So with this information in mind, it now says to find the inverse of this function. If you're coming up with the equation, it says you can find the inverse of f of x by using the switch and solve method. So you probably did some of this in Algebra 2. But remember, all you have to do is switch the x and the y in the equation and solve for y, and that's going to give you the inverse of your original function. So if I look back up here, here's my x in the function. F of x, remember, is the same as y, right? So what they're saying is just switch their places. So if I did that, I'd have x is equal to y minus 2 quantity squared minus 3. So if all you have to do is come up with the inverse equation, if you switch x and y and solve for y, that will give you the inverse equation. So I'm trying to get the y by itself. So I'm going to solve this just like I would any other equation. What do you guys think we should do now? Add 3. Okay, we'll start there. So I add 3 to both sides. So now I've got x plus 3 is equal to y minus 2 quantity squared.
Square root.
Take the square root, right? Because I can't take anything out of that parenthesis as long as it's got that square around it. So now I've got the square root of x plus 3 is equal to y minus 2. Now what should we do?
Add 2.
Add 2. All right. Now over here, remember whenever I add 2, it's not underneath a square root, right? So it'd be x plus 3 under the square root plus 2 equals y. Or if you flip everything around, you'd have y equals the square root of x plus 3 plus 2, right? Okay. It then says that it wants us to graph the inverse. Okay, well, I can go about that a couple ways. I could plug some points into this new equation that I came up with, right? And then that would give me some points to plot. If you remember what an inverse does to your graph, you could reflect the points from the first example in that way. Or you could fill in the table by doing exactly what they said to do here, which was to switch x and y based on the points from above. Okay? Doesn't matter to me which way you're thinking about it. Go about it in whatever way works best for you. Let's say we didn't remember how your inverse reflects your graph. Maybe we don't remember that at all. Then we'd want to do something with either the equation we came up with or this switch and solve method that they told us about, right? Okay, so if I were to just pick some values, then I could plug those numbers in here. So let's say if I look back up here, all my original y values, which whenever I switched x and y would technically be like my x values, only were between 1 and negative 3, right? Well, let's say that we were to plug in negative 3 for x in our new equation. Okay, let's say we're going to use that as our first point. Then under that radical, I'd have negative 3 plus 3, right? And then there's a plus 2 on the end of my equation. Well, what is negative 3 plus 3? 0. Okay, and then the square root of 0 would just be 0. Plus 2 is 2. Okay, so when we plugged in negative 3, we got out 2. Okay, so for this, we would have the point negative 3, 2. Or if I wanted to come put that on my graph, 1, 2, 3, 1, 2. Okay. All right, and then if I look back up here, we had negative 2 as y values twice. So let's try plugging in negative 2 and see what we get as an outcome. Negative 2 plus 3 underneath our radical with plus 2. Okay, so what is negative 2 plus 3? 1. Okay, so I'd have square root of 1 plus 2. What is the square root of 1? 1. Okay, now remember when I take the square root, I'm asking myself what multiplies times itself to give me that number, right? Is 1 times 1 the only thing that gives me 1? What else?
Negative 1.
-1 times -1. So really, this is positive or -1 when I take the square root, right? Plus 2. Okay, so what would 1 plus 2 be? 3. Okay, so it gives me the coordinate point -2, 3. What about -1 plus 2? 1. So it also gives me the coordinate point -2, 1, right? Depending on if I use the positive 1 or the -1. Okay, so if I were to go plot those points, I got one at -2, positive 3, and at -2, positive 1. Okay? And then the only other y value from our chart, which since they said to switch, we're kind of considering as our x's, was 1. So let's try plugging in a 1 underneath that radical. So 1 plus 3 under our radical plus 2. Okay, and what is 1 plus 3? 4. And what's the square root of 4? 2 or -2. Okay, so plus or minus 2. And then we got a plus 2 here, right? Okay, well, what is 2 plus 2? 4. Okay, so I could get 4 as one outcome. If I use the -2, what's -2 plus 2? 0. So that would give me the point 2, 0. So I'd have a point at 2, 4. And a point at 2, 0. All right, so I'm going to go list those in my table over here. So here's my x and here's my y. So if we started down here with this point, this point down here, so you can see which one I'm talking about. That one is at where? 2, 0, okay. All right, and then we have this point here, which is at -2, 1, okay. And then we have this point out here, which we said was at, and then we've got a point up here, which is at -2, 3, and then finally this point up here, which is at 2, 4, right? All right, so looks like the table is all these points, that we just came up with by plugging in some values, right? Okay, so if I were to come up here and look at my graph, they look pretty similar, right? What seems to have happened here to the graph from the first example to the inverse graph?
Will the points be at 1, 0, and 1, 4?
1, 0, 1, 1, 4. 1, 0, and 1, 4. Oh, yes, because we used a 1, not a, sorry, I apologize. Thank you. We used a 1, not a 2 there. Okay, yeah, we did plug in a 1. Okay. Okay, so we've got our graph here that looks very similar to what we started with. But what appears to have happened to our graph? The x and y values flipped. Okay, so if the x and the y values flipped, what type of reflection might we say happened here? It didn't just reflect over the x-axis, right? It didn't just reflect over the y-axis. Both, right. It reflected across the line y equals x. Very good. So if you were trying to just change your graph, you could just reflect your points across the line y equals x. In other words, that's going to flip your x and y values. Okay. Now, my first picture up here, was this a function? Yeah, what makes it a function? Yeah, the vertical line test or the x's don't repeat, right? Okay, what about this picture? Is this a function? No. Why not? Right, right. And then all those decimals occurring in between there, right? Okay, so what do you guys think we could have done to the original function so that we could have made sure this one ended up being a function? What do we think? Or think about it this way. This is a square root function, right? What am I not allowed to be taking the square root of? Negatives, right? It doesn't work, right? Those don't exist. Okay, well, our function, just like before, has been shifted some, right? Okay, it normally would have had the vertex right here, would have normally started at 0, 0, right? But it's been shifted over and up some. Okay, so that would basically mean that anything below this point, if it would have been at 0, 0, wouldn't work, right? Because it would have all been negatives, which we're not allowed to have. So basically, I would have wanted to get rid of this whole part. That would have been underneath my x-axis, right? Okay. Well, since I switched my x and y's, what part of the original function would I have been getting rid of then? Which side of it? So the one on the bottom here, which part of this picture would that be equivalent to? The left side, right. Since I switched the x's and the y's, I get rid of the left side. Okay. So if I was trying to do that, if I was trying to get rid of the left side, then that should help us answer some of these questions down here. So for our new function, this one that we just drew, in this picture, what would you guys say that the domain of this picture is once I restrict or even before I restrict that piece off of the bottom? What's our domain in this picture? It goes to the right, but it's not continuous to the left, right? So what's the furthest that it goes over there? There we go. So x is greater than or equal to -3, since that is a solid point right there at -3. Okay? And you guys said that this was not a function as it was originally drawn, right? And your guys' reasoning was it didn't pass the vertical line test, which meant that it had x values that repeated. Okay. So if I wanted to restrict my range to make it a function, we said we'd need to get rid of the bottom half there, right? Okay, so if I do get rid of this bottom half that we talked about, then I'm getting rid of everything below this line. So what would our range be if I get rid of that bottom half of my function? Y is greater than or equal to, yes, to 2. Okay, because we got rid of that bottom half there from the function. Okay? Okay, and then like you guys said, when I asked you what did you guys notice about the tables, you guys said the x and y values just switched from this table up here to this one down here. So x and y values are switched. Okay. Okay, so originally, before I restricted this bottom half here, my range would have been all real numbers, right? Because we would have had an arrow going upward and an arrow going downward. But like you guys said, if I want it to be a function, I have to get rid of the bottom half, which means I'm going to have to restrict my domain. From my original function, which would be the range of this function. So like you guys said, up here, that's equivalent to the left. So I would either restrict the left side's domain on the original function, or what that really does to our new function is restrict its range, since we're switching the x's and the y's. Okay, so quick recap here. Whenever we want to change what the graph looks like. So if I have some graph and we are trying to create its inverse, we said we don't reflect across just the x. We don't reflect across just the y. We said we reflect across what? What did you guys tell me a second ago? We said to get from this picture to this picture, I didn't just flip it across the x. I didn't just flip it across the y. It looks like we flipped it across, both. So we said over the line y equals x. So by reflecting over the line, y equals x, which basically means switch your x's and your y's. Okay? For a table of values, if you are given a table and asked to come up with the inverse table, what are you going to do to your values? How would I get from this table to this table? Switching them. Good. By switching x and y values. All right, and then lastly, if they give you the equation. Okay, and that's what we were asked to do in this first little section right here. That's what we did right here. If I was asked to come up with the inverse, what did they tell us we could do? What did we use to, what did we do? Switch and solve method. Good. That's exactly what they had us do by using the switch and solve method. Okay, so you know how to take a graph and give its inverse. You know how to take a table and give its inverse. You know how to take an equation and give its inverse. So that's exactly what we are going to do with our sine, cosine, and tangent. So if you flip it over onto the back, they have a place for you to write down your tables for sine, cosine, and tangent. Remember, in our tables, the top row is x, the bottom row is y. So these are x's and y's for all these tables. Okay, now, typically for the parent function of sine or cosine or tangent, we normally go from 0 until a cycle is complete, right? We start at 0, go to 2 pi for sine and cosine. For tangent, we start at 0, we go to pi. However, if I look back at the graph, did I start at 0 on this function and just graph this direction on the original? No, we graph some on both sides of 0, right? So anytime you're coming up with what a function looks like, you want it to be evenly balanced across what would be your 0, right, your origin. So for all of these, we are going to graph or put in points from negative pi to pi instead of from 0 to 2 pi. That way we've got some on both sides of our 0, okay? Now remember, you're not expected to have memorized from negative pi up to 0, but you've got from 0 to pi, and then it's just repetitive, right? So you can fill in the second half of your table and then go back. So like in this table, you'd put negative pi halves, 0, pi halves, and pi. All right, so this first one is for sine, right? At 0, what is the y value for sine? 0, yeah. Starts at 0, 0. Okay? And then from 0, my sine graph at pi halves goes up to the maximum, which if it hasn't been transformed any, it'd be at 1, right? And then when I get to pi, I go back down to 0, right? And then the other side should continue our pattern, right? So I went 0, 1, 0. Then at negative pi halves, I would be at my minimum, which would be -1. And then when I'm back at negative pi, I'd be back at 0. Okay? So you're just going to go plot those points on your graph. Okay? And then you are going to tell me what the inverse function would be. Okay, well, you started out with y equals sine of x, right? And how did they say you get a new equation? Flip the x and y. So this would be the same thing here as x equals sine of y, right? Well, just like when we reviewed geometry and you were solving for theta, we said you do what to get rid of sine on one side of the equation? Use the inverse, exactly. So I would just take the inverse, which would be sine's inverse of x equals y. Okay? And then what did we say you do to come up with your new table of values? Right. So when I go fill in this table, I'm just going to switch these two rows, and then I'm going to graph those. Because it says graph them both on this picture, and then you just tell me what the domain and ranges would be. All right? Okay, so there is no separate page. This is the assignment. This is it. So you've got the rest of the period to fill this in. Okay?